This is Lab 1, Part 2, brought to you by Bad Kitty. And in this demonstration, I'm going to build a voltage divider on a prototyping board and demonstrate how the voltage drops literally across each resistive stage in the series. In this demonstration, I'm going to be using two digital voltmeters. The first one is going to be in the voltage measuring mode, and the other one will be measuring resistance and supplying a voltage. I've given you photographs of prototyping boards in previous lectures. I'm just going to review here quickly. So a prototyping board or a breadboard is a plastic block with holes drilled in it. Behind the holes are copper strips. We'll go through this a little bit more detail. And usually mounted on the plate are a couple of banana jacks for making connections to power supplies. So to work with one of these, and this is one of the small proto boards in the laboratory, I could designate the two jacks as high and low by plugging into a voltage source. Usually on the proto board, there are what are called bus connectors, and these are long arrays of 5 holes attached in common to a single copper strip. So a copper strip on the first row at the top, a second copper strip along the holes in the bottom of that row, and all of those holes, if you plug in a wire, would give you a contact. So to set up the thing, what I would normally do is apply high and low voltages or potentials to the connector jacks, and then I would run wires to the bus lines to give me, at the protoboard surface, a point or a group of points to get the high voltage and the reference, namely the low. Just as a point of reference, I can get, if I have a big project, I can have a breadboard system that has many rows and proto breadboarding areas. That's the one on the left. And the device on the right is a fully functionalized, essentially lab kit, which has the breadboard in the middle, a number of bus lines, and then some functions built into the chassis surrounding the breadboard. Returning now to the small breadboard, which I'm going to use for the demonstration, I have in the middle the so-called breadboard area, and these are independent copper strips under 5 holes each, and this is where you build the prototyping circuit, or the prototype circuit. You'll notice that the breadboard area is actually surrounded, or usually surrounded, by sets of bus connectors, and at the bottom of this particular slide you'll see that these group of resistors that are in series have been connected to the bus lines for potential experiment. So one of the buses, the one at the bottom, has a black jumper cable or jumper wire connected to the row of 5 where the first resistor on the left is plugged in, and then there's a red jumper wire going from the top bus connector to the other end of the resistor series. So the breadboards are organized in rows or stacks of 5 holes, under which those 5 holes are a copper strip that's independent from all the others. So if I mask out the breadboarding area, you see 5 holes that are arranged in a stack or a row, depending on how you orient the breadboard. Those 5 holes are connected to a common copper strip at the bottom, so anything that you plug into those holes are going to be connected by making contact with the copper bar underneath. What you'll find is that the rows are arranged in 5s spanning a trench. So below what I just used to mask out is a trench. So in the breadboard that you've got in front of you, I'm putting resistors in series in one set of 5 rows, and I could have a second set up parallel in the one above it. So a cartoon representation of those 5 holes that are in an array. Top view, you see 5 holes in the Teflon block. If you were to slice through that, you would see the 5 holes leading to a copper strip at the bottom of the hole. And then if I had X-ray vision from the top, I would see the holes looking down onto the exposed copper strip at the bottom of the Teflon block. The point of all of this is to plug in small circuit elements without actually having to make solder connections or permanent connections. So I can play around with and reconfigure my circuit until it works. And then after I've got a circuit that works in the prototyping area, take it, put it to another board, and actually do the soldering and make the thing permanent. So at the top left, I've got a representative cartoon of a resistor. Imagine that I have one that's red and one that's blue. And if I wanted to connect those red and blue resistors, I would plug them into the same row of 5 and they would make contact. So the red one on the left is facing away from you. The one in blue is facing towards you. I would make a connection between those 2 resistors. Here's another view of the same thing from the top. So I add the red and the blue resistors, plugging them into a common row of 5. And this is actually what it looks like in real world. So I have those 2 resistors plugged into the same row of 5. And that makes they're now in electrical contact with one another. No soldering, and I can swap out things as I need them. For my demonstration of a voltage divider, I'm going to take a series of resistors arranged on the prototyping board, and I'm going to attach to these resistors the DVM, the first one being in resistance mode, which I know is going to act like a battery trying to apply a voltage to the 4 resistors, or the device under test as we would call it. And then I'm going to measure the voltage at each junction between resistors using a separate voltmeter. So it's an easy way to do a demonstration. So my first step is to attach the DVM operating in resistance mode to the 4 resistors that are arranged in series. And the meter is telling me I have a composite resistance value of all 4 of those resistors equaling 6,367 ohms. I'm now going to attach the second DVM in voltage reading mode to measure the voltage being applied to those resistors. I now do that, and I see that the total voltage applied to the device under test, namely those 4 resistors in series, is 631 millivolts. I'm now going to move the red cable going to the voltage reading, the DVM reading voltage to each of the junctions along the series resistors. So at point number 1, namely the junction between the first and the second resistors, I measure a voltage of 454 millivolts, which means that I've had a voltage drop of 177 millivolts across the first resistor. If I move the red lead to the junction between the second and third resistors, I measure a voltage of 277 millivolts, meaning that I've had an additional voltage drop of 177 millivolts across the second resistor, giving a total voltage drop between the first resistor and the second resistor, namely the 2 of them together, of 354 millivolts. If I now move the probe, the red cable, to the junction between the third and the fourth resistor, I see a voltage of 177 millivolts, which means that I've had a 100 millivolt drop across the third resistor and a total voltage drop from 1 to 3 of 454 millivolts. And finally, if I move the probe to the end of the resistor series, I get a voltage of 0, which I should see because that's the reference point. And that means I had a voltage drop of 177 millivolts across the fourth resistor in the series. and a total of voltage drop of 631 millivolts across the entire set of 4. If I now look at the device as a voltage divider, I see that I can get 631 millivolts by connecting to this position in the set of resistors. I can get 454 millivolts if I connect to this particular point in the set of resistors. I can get 277 millivolts if I connect to this position. I can get 177 millivolts if I connect to this last position here in the series, so above the 4th resistor. My point of reference is the end of the series. And if I look at those numbers, I see that I was going in 177 millivolt steps through a couple of the voltage drops, but one of them was 100 millivolts, which means that domino swiped one of the resistors and replaced them with another. So I had one resistor that was not the same as the others. Devious cat. Since I want to confirm my suspicions of feline sabotage, I measured the resistance values of each of the resistors in that series array device, voltage divider, whatever you want to call it. And indeed, I have confirmed that resistor number 3 has a value that is significantly different from the other 3, being 1,000 ohms or 1,005 ohms compared to 1,789 ohms. So I confirmed that Domino did actually put in a sabotage resistor. If I now can calculate the total current through the 4 resistors based on the total resistance measured and then the voltage that's applied to the device, namely the 4 resistors, using the second meter, I did calculate, using Ohm's law, the total current of 0.0992 milliamps. If I now use that, multiply that current against the individual resistance values, I get the voltage drops, the calculated voltage drops for each of the resistors, and they confirm what I measured. If you do the calculations that I've just described, and I suggest that you do as practice, note that I rounded up the values to 3 significant digits for convenience purposes, and then also to match what the meter reads out.